Recording. Okay, so thanks for coming to class 9, right? Yes, class 9. We have this class and then 10 and 11 left. Let's go over the muddiest parts from last class. So previous class, we went over part 7, which involved learning about lists and functions and a little bit of an introduction to purrr, which is iteration over lists. And so some muddiest points, there were people brought up the indexing of lists and vectors versus matrices, the bracketing essentially. And yeah, I agree that is odd and confusing and hard to keep straight. I try to write in some homework problems that might help with that, and I'll use it again today. So we'll go over that again today. But yeah, I think that takes a lot of practice. It is odd syntax. The functions, some people found confusing, and I want to do that basically every class from now on. We'll have more function examples, so hopefully that will help. Someone did point out, they asked if you could return multiple things or outcomes from one function, and that is a yes. I meant to actually include that in today's class, and then I didn't, I forgot. So this is a good excuse to talk about that now. So this is, I'm making a kind of a trivial function here, my new fun, and the function takes one vector, does a couple things to it. It calculates the mean of the vector, the length of the vector, and then the return is a list. So the way that you would return multiple objects from a function is to use a list, which we just learned about last class. I tend to use a named list, which means you specify the name of the object. So you put the name on the left and then what you're returning on the right, the name on the left, what you're returning on the right, and the name and then the thing you're returning. And so the name here is mean, which I've returned the v mean, which is one number. It's the mean of the vector. I'm returning the length, which is one number, the length of the vector. And then I'm also returning the input vector. So I'm returning back what the person put in the function, which was the original input vec. And so we can see an example of using this. I just created a length 4 vector, 1, 4, 2, 40. It's a numeric vector. And then I ran that function on it. So that's my input, that vector. And looking at that, we can see that there are 3 elements to that list that's been outputted. The $ tells us that that's the name of the first element of the list, which was the mean, and that's 11.75. It gave me the length, which is 4, and it gave me the input vec, which was the original thing I put in there, the original vector. And so I could call out, I saved this output as my out. I could ask for each of those elements with the $, or I could have used the double brackets if I wanted. I tend to use the $, if they have names, just because I'm used to doing that, but you could do that either way. And so when I pull out just the mean, it just gives me that number, 11.75. And if I pull out the length, it gives me the 4. And if I pull out the input vec, it gives me that original vector. And so I'll try to show more examples like this later. I don't think I have one today, but it is very useful to be able to return multiple things, multiple types of objects from your function. This one is more of a note, just if there's anything that's still confusing, please definitely reach out to me or Colin. And I think if you're new to R, especially if you were new before this class, it just takes practice to keep struggling and keep succeeding over and over again. I think this class isn't really sufficient to get someone super comfortable with R. If you're brand new to R, I think it just takes time on your own. That's kind of why I try to put questions in the homework that are a little harder, just to help you kind of have to look up the documentation or struggle a little bit, because I think that is kind of the key to making it click, is just writing your own code over and over. But while we're here, I think it's good to ask questions and see if one of us can help clarify anything that you need. So please reach out. Clearest points, I just like that someone was excited about learning about functions, because I also think they're the most useful part of R, and that purrr is becoming a little more clear. We're going to talk a lot about purrr today, so hopefully that will help. Hopefully it doesn't add more confusion. And there was a note about creating functions during class. I think I'll try to keep doing this, basically create a function in live time, because this idea that usually we have code already written and that we want to create a function out of that, I think is very useful to see someone do. And so hopefully that helps, just to see the kind of thinking process behind creating functions, because I think in terms of analysis and data cleaning, that's usually what happens, is you have a bunch of code and you realize, oh, I need to use that again. How am I going to make that a function? And that again will take some practice. Any questions besides those? There was a note that I forgot to give you all a break last time. Sorry about that. Definitely remind me if I haven't done that. Sorry about that. Clearly this class takes like all of my brain power and I have a hard time remembering to record. So thank you for reminding me to record and give you breaks, but I can't even, I lose all of my fast abilities to do anything and talk apparently. So I will stop talking about muddy points. Oh, and then the last thing is the final. So I haven't finished writing the final yet. I had intended to do it by today, but I did not. I think I'm going to try to do it by Friday. So what I decided was that the final will not be a project really, but more of like a bigger homework. So I think I will not assign any more homeworks and just assign the final on Friday and have it due in 2 weeks. And I will give you the data. It will basically be similar to the homeworks, but just longer and a little bit more involved. And that was the best I could come up with. So hopefully that works out. Let me know if you have any misgivings about that. I think it's fun to do a project, but I know finals time can be kind of overwhelming and I don't want to like stress anybody out. So I'm working on that. I will let you know when it's up. And I will try to include some practice with purrr and lists in there too, because I won't be able to give you homework on that stuff. And I think it's good to practice. I also will probably kind of print out, kind of like the homework from last week, where I show you the plot and I show you the output. I will try to do that as much as possible, just so you have something to kind of aim towards and know that you're on the right track. But yeah, let me know if you have any questions about it in the meantime, or if you have feedback about anything. Okay. Oh yeah, someone did just ask that. Hopefully, did that answer the question about the final project? Are there any other questions, seeing as it doesn't exactly exist yet? It's in a work in progress. Oh, I will make it due. So it depends on when I get it up. I think I will make it due the Friday of the last week, because grades are due like a week from then. So let me see, what day is that? The last week of class for school public health, I think for everyone at OHSU, is the week of the 14th. So we'll have class on the 16th, and then I will have the final due on the 18th, which is Friday. So you'll have 2 weeks to do that. Any other questions? All right. Okay, so we are on part 8, which is going to have a little bit of statistics, a little bit of broom, which relates to statistics, and then a lot more purrr. So part 8 is up on Dropbox. There are some data files that we've worked with before and a couple new packages in here. So make sure you run this if you need to install anything, just a couple, I think. And so today we're going to talk a bit about statistical modeling, fit a couple simple models. Next week we'll be doing more statistics stuff, and just kind of seeing how that works in R. We're going to learn a little bit more about map and different what we call type specific versions of map from the purrr package. We'll learn about how we would essentially use purrr on data frames. So what that means really is we take a data frame, we split it up into a list or create what we call list columns, and then we iterate over those lists. And so that can be kind of a nice workflow for dealing with different pieces of data. And we'll also learn a couple more purrr functions. We might not get through all this today, probably not actually, but we will just finish it up next week if we don't, so it's okay. All right, so I'm sure most of you, I know most of you have done statistics in R because you took Intro to Biostats, though not all of you have. And so you've probably run many statistical tests or models in R. But I do want to just give everyone, make sure we're on the same page, a little brief intro to how we would fit a model in R. This isn't meant to be, I'm not going to teach you about the statistics theory behind all this stuff. I just want to show you how you would implement some basic methods, but you'll need to read some more if you want to really learn how to do this stuff right. So I linked a couple free online books that are kind of half statistics, half R. These are both, this one is very statsy, has a lot of really good explanations. This one is a little bit more about inference. So they're both really nice and freely available for background reading. So if you have done R, I mean, most of you were lucky and had Micah this year, and she probably taught you some really nice kind of tidyverse ways of doing statistical models. I'm sure she probably also showed you broom examples. But if you've taken a stats class where they didn't really teach in the tidyverse, you probably have seen kind of how there's a very large variety of ways that models are run in R. And by that, I mean like the inputs often are not standardized across different types of models. The output often looks quite different across different models. And so we'll show one, linear regression, kind of the simple regression model. So linear regression uses least squares estimation to fit the best fit linear line to a model. You have your outcome, which we sometimes call Y. You have your covariate or your independent variable or predictor, whatever you want to call it, X feature if you're a machine learning person. And the model has an intercept, it has a coefficient, and then it has an error term. And so how that's kind of the stats way of writing it, but how that translates to R is that we use the formula way of writing things in R. And so a formula in R always has this tilde, and we have on the left side our outcome, and our X is our predictor. That's our column name for the predictor is on the right side. So it's like Y is regressed on X, basically. And here I have outcome predictor. If you have multiple predictors or covariates, you would just add them up, unless you want an interaction term, which we'll talk about more next week. But in general, this is the kind of standard way to write a regression model, at least. And the function we use here is LM, and LM stands for linear model. LM is actually in the stats package, but when you turn on R, it loads a few packages for you that you don't actually have to call. You don't have to say library or pload stats. It just is there. So just as a side note, it's in that package. And so we have the Palmer penguins data. We'll use that. And we want to look at whether species and sex are associated with body mass. So body mass is one of the continuous values. And that's going to be our outcome. So that's going to go on the left side of our tilde. And then our categorical predictors are species and sex. So we could also have had a continuous predictor, but here I just chose two categorical ones just for example. So just remember, if you haven't done linear regression in a while, or if you don't know much about it, the estimates that we're going to get out of this model that correspond to these categorical variables are going to be interpreted as the expected mean difference of body mass. So that's our outcome compared to whatever the reference group is. The reference group in R is by default the first category when you alphabetize them. So if you think about when we turn something into a factor, how the default levels are in alphabetical order. So it's the same idea. The first level or the first category is your reference group. And next week, we'll talk more about how to change your reference group. And that's reference group is another word for like comparator group or control group or something like that. So we'll talk about that and how to change that up with factors next time. But we're just going to deal with whatever our default is in R. But if you want to know more and hear a better explanation of all this, definitely read the linear regression chapter in this book, and also look at the documentation. Actually, why not I just pull it up for now so you can see. There was a comment I saw someone put in the survey about having trouble reading the documentation, and I totally get it. It's not great half the time. So I think like LM is obviously a basic function that's been in R for decades. So no one's really updating this documentation. But you can kind of get a sense of what the arguments are. Usually the first 2 or 3, yeah, I would say in general, probably the first 1 or 2 arguments are the ones we really care about. And the rest are going to be pretty optional. So for example, in this case, we do need to specify our formula, which is going to give us our model. And if we're using variable names like column names, we do need to specify our data so it knows where those columns are coming from. Seeing things like subset, we're not going to do, that's specifying if you want to run it on a subset of the data, or weights if you are doing like, it depends if you're doing survey weights or something, I don't know. And then a lot of this stuff we just leave it as the default. I don't know if I've mentioned this. A lot of functions have this ... at the end. And that's just often means that you can add in additional arguments, and it's going to tell you where those arguments are going. In this case, they're going to other regression fitting functions, which is a little bit nonsensical. And we really don't need to worry about it for LM. I'll try to think of a better example where this is useful, but sometimes in plotting, I would say, is when I find these ... to be more useful. Mostly you'll be able to see it in the examples if it is something that people do a lot. But here, these examples are pretty basic, so they're not actually that helpful here. But you can see essentially the way we use LM. This is like the most basic way to specify a vector of an outcome and a vector of your predictor. And so that's what we're going to do here. Here I have the code, LM, the formula. We have body mass G is the name of the column of the outcome. Species is the name of one of my predictors, and sex is the other one. And I do need to specify data equals penguins. In this example, they don't have data equals something because they've just defined the vectors outside of a data frame. So they don't need that, but here we do. And so if we run this, I've saved it as an object, so fit LM, so I don't see any output. So to see the output, I enter fit LM. And this is what you get. This is because this is a special kind of object. It's not it's essentially deep down, it's a list, but you don't really see that here because of the way that it's printed out. This is a special linear model object. As I mentioned a while back, R is an object-oriented programming language, which means you can create different types of object classes and define like a print statement for it, a plotting function, a summary function, all these functions take a linear model and do something special to it. In this case, when I type out the name of my linear model object, I get this printed text. It's telling me the call and the coefficient estimates. So it's giving me the intercept estimate, the chin strap versus Adelaide, which was Adelaide is our reference group, Gen 2 versus Adelaide, and then sex male means male versus female. And you'll notice that this doesn't even give us information that we usually want from a model. We usually want the estimates, and people usually want to see the p-values or at least confidence intervals. So the way we get the p-values is by calling this function summary on top of summary on that linear model. And if we look at what is the type, what type of object is this? We can see it tells us LM, which means it's a special kind of object. And there's other functions such as plot LM. I commented this out because it's a little bit of an interactive thing. These are the diagnostic plots, and it wants me to hit enter, and it's showing them to me in my plot viewer thing here. So that looks good. It's categorical data, so these look kind of funky, but that's basically what you get out of it. So it seems nice. You get a lot of information. It's sort of not intuitive that you need to call this summary function to pull out more data. This doesn't give you the confidence intervals. You do need to use another function to get the confidence intervals out. So it's a little bit of like jumping through a lot of hoops. So I added in the like built-in ways of getting confidence intervals out. If we want to pull this part as a table, we need to take the coefficient function of the summary. Here we need to get the confidence intervals out. It's not pretty, I will say. So those are like the default base R ways of pulling out information, but there's actually a package that was developed a few years ago called broom. And I say here that broom is truly a life-changing package for statisticians, and it really saves so much time. I cannot express how much time I've saved in my life now because of broom. Because what it does is it pulls out information from any kind of model, most kind of models, in the same exact way. So if I want, say, to run a linear regression model or a logistic regression model or a grouped lasso model from some machine learning method, tidy is going to pull out the information that I need, this function tidy inside broom. So there's three main functions in broom: tidy, glance, and augment. And tidy is the one I'll focus on the most, pretty much 90% of the time. Glance can be useful. And augment, I'm not going to talk about today, but maybe in the later classes. So tidy is where you would get the kind of basic information about your model, such as coefficient estimates, confidence intervals, p-values, etc. Glance is named glance because it's like a glance of the model, which are summary measures on your model. For instance, in linear regression, you'll get R squared, log likelihood estimates, AIC, BIC, things that describe your model. And then augment is going to help you make predictions with your model when you have new data. So I haven't talked about that in this section yet. And then what broom does is it takes as an argument your fit or your model object. So in this case, I saved that linear regression as fit LM, and then we run tidy on that. And it gives me by default this. Oh, I just realized I should save this as my own file, sorry, before I change anything up. Okay, so what we see here is a tibble, 4 rows, 5 columns. It has these as terms, which are defining our terms in the model. We have an estimate, standard error, statistic, and p-value. So this is nice because it gives us a nice data frame tibble to work with if we need to. And all we have to do to ask for confidence intervals is include an argument conf.int equals true. And that will then give us 2 more columns, same as above, but now we have conf low, conf high. So what this is telling me is, for instance, if we look at sex male, the expected mean difference comparing males to females in body length. I already forgot what I'm doing. Body mass is my outcome. So males tend to have 667 on average. Their body mass is 667 milligrams, grams, sorry, I should really know this, grams more than females on average in our penguins data. And if we want a confidence interval on that, the lower limit is around 600 and the upper limit is 735. And that's going to be just a 95% confidence interval by default, but you can change that. And so the nice thing about having this out just in a tibble is that we can actually then mutate it. So I'm going to save that output here, save it as a tibble. LM tidy output is now that tibble down here. Here I'm going to use a function called p-value that's in the scales package, just to show you quickly how I use that. What it does is it takes something like this, a number that's a p-value. You can look at these p-values, like this one is 4e to the negative 258. No one's going to care about that level of precision. So it's common to transform p-values using, first of all, pick how many digits you want. So in this case, I'm going to say 3 digits because my accuracy that I'm telling it is 0.001. And then anything below that, I'm just going to say less than that number, since it's typical to write out p-values like that. So if I enter scales p-value and I put this 0.2354464 in there, I get 0.235, which is the 3 digits, like I was saying. If I put something that's less than my accuracy number, this is what happens. You end up with a character string. Well, both of them are a character string. Let me show you both at the same time. Here is a character string after rounding to 3 digits. Here is a character string after turning it into less than that accuracy number. So you probably, if you've read publications, you've probably seen things like this where they don't bother to say super small p-values, they just say less than some number. And so if we do that, here I'm taking my LM tidy output, I'm selecting the columns that I'm interested in, which are the term, which tells me which coefficient estimate it is, the estimate, the confidence interval limits, and the p-value. So I'll just show you what that looks like. So that's my tibble. But then I'm mutating. So I'm mutating p-value. I'm using that scales p-value function on the p-value and using the same accuracy. So I'm going to convert that to a character string. And then I'm going to mutate across where is numeric. So that means these 3 numeric columns, I'm going to round to have 1 digit. And then I'm going to use GT, which makes that nice table in an HTML table. So we can see I have rounded my numbers, so it's a little bit easier to read, and p-value is nice to look at. I guess I should show you another, just as a side note, like even this p-value is written in scientific notation. I have a really hard time if even just thinking about this, like, is that 0.05, is it 0.5? I should be able to see that a little easier, but I just like to clean it up. So now I can see it in real number speak. So that's a nice table. You'd probably want to change the terms. If you're putting this in a paper, you wouldn't show the intercept, first of all, and then you would probably rename these somehow, probably using case when or however you like to do that. But that's a start. Just to show you glance. Glance, as I said, is going to give us summary statistics essentially about our model. So I use as the argument our fit, the linear model fit. And we can see R squared is quite high, adjusted R squared. I think this is the p-value probably from the likelihood ratio test, I think. And then AIC, BIC, all this kind of stuff. Number of observations, which is useful sometimes. So you get these information. Sometimes people report R squared or adjusted R squared. So that's an easy way to pull that out of a model. Or if you're comparing different models, it's a nice way to get that information out. And then another brief intro that I will again talk about next week more in depth is this package GT summary. I think I used GT summary on the first day of class just to show you a brief table. It's like kind of like a table 1, cohort a description table. And I'll show you more of those next week. But GT summary also has functions to summarize regressions and other models. So table regression, table underscore regression, is a function that will take as input the linear model fit and give you a little prettified table. So you can see, oh, I'm saying forever, it's weird. What it's done is essentially made the table from that I just worked so hard to create up here, but did it in one line and made it look nicer. So what they do is they pull out your, by default, You can change all these things, but beta is your estimate. And then 95% confidence intervals. P-value even gives you a footnote. The confidence interval is CI. You can see the reference group, which is nice. It by default prints that out. So Adelaide was the reference group for species. Female was the reference group for sex. So that's a really nice, easy way to get out all the relevant information from your model. And there are many kind of helper functions, which I'll go over next week a bit more. One that you might want to use here is called add global P. So you can see that when we have a 3-category predictor, Adelaide, Chinstrap, Gin2, they're all being compared to Adelaide. So this p-value is testing whether this beta is 0, which means the mean between Chinstrap and Adelaide are not significantly different. Gen2, however, does have a much higher mean body mass on average than Adelaide, and so that one is individually significant. But sometimes people want to test that predictor as a global test, which tests whether there is any effective species. And so you would add the global P with that function. It's not going to make a difference for sex because sex only has 2 categories. If you've done ANOVA, yeah.
So this is, I don't want to throw you completely off your train of thought, but there are characters that are missing in when I'm trying to run the same exact script. And I'm wondering if I'm missing a library there, like with the Adelaide, I'm not getting the minus, and my p-values are showing up in different places. And it's also just taking me a lot longer to run these programs or these scripts.
That's interesting. I'm not sure why that would happen. It might be another library. It might just be Mac versus PC. I'm not sure. There might be some kind of helper HTML conversion library that's in there that's not installed or maybe not updated. I can look into it, but yeah, I don't know. Sorry, I don't know how to answer that right now, but that's an interesting question. Yeah, I'll look into that. Any other questions?
I have a question. If you were doing a logistic regression instead of a linear, would all of this stuff pretty much apply? Just like the LM would be different, yes. Or
you would use GLM. So GLM is going to be generalized linear model. I almost put a logistic regression in here, but then I decided I didn't want to do that today, but next week we'll talk about it. But GLM is you can actually fit a linear model with GLM because it's generalized linear model. So that would work. And it would work the same way. You could put the GLM in here and it would give you odds ratios. Well, actually it would give you log odds ratios. You could ask for odds ratios if you wanted to. There's a setting. But yeah, it's very, very similar. Similar in the format that you load the model as well. Where is it? Where'd it go? Like this. So GLM is used the same way, except you'd have your binary outcome here. And you would also, in generalized linear models, you can fit like Poisson models and logistic regression, log linear models, etc. So you do have to specify which one you're doing with this argument called family. But yeah, we'll talk about that next week because that is a very common thing. And Cox models too. You can do that in R. I was going to talk a little bit about that for survival data. Any other questions? Okay, so that is very, very, very brief introduction to linear regression. The other kind of super simple test that I just want to show you. So that was more of a model, fitting a regression model. There are also a lot of different tests that you might run, like t-tests, chi-square tests, Fisher exact tests, etc. There's a function for all of those tests. And like I said, they all kind of use different syntax. Chi-square test especially is odd because you have to make a 2x2 table. And we'll talk about that next week as well. But for t-test, which is comparing the mean, similar to linear regression, you're looking at means, but in this time you have only just 2 groups. And you're comparing the mean of a continuous numeric vector between those 2 groups. So in this case, I've just pulled out sex as my grouping variable. My outcome is, again, body mass. And so that means that you have, again, an outcome, essentially. You can think of your numeric vector as your outcome, and you can think of as your categorical vector as your predictor, essentially, even though it's not really set up like that the same way that it is in a linear regression, but that's how the formula works in this sense. So in this case, the null hypothesis for a t-test is that the two means are not equal. So between female and male sex penguins, the body mass is equal, like there's no difference in the mean body mass. And the alternative hypothesis is that they are different, that they are not equal. So t-test and t.test is the name of the function. There are a lot of arguments. So let's look at those just to see. So t.test, there's actually two ways to perform a t-test. I'm using this way, and then in a minute I'm going to show you this way. But the first way that I'm doing it uses a formula again. And then there are other options that in this case are kind of useful. So you might want to do a paired t-test if you have paired data, like if you're doing a before and after test, for example, on the same people or same subjects. Usually you want to specify whether the variances of your numeric vector in each of your groups are supposed to be, we assume, equal or not equal. By default, this uses the not equal version, var.equal equals false by default in this function, which means it's assuming that the variances are not equal between sexes, which I think is much more common situation, but you can change that. And you can also change whether you're doing an alternative two-sided test, less than test, greater than test. So you can specify things like that in here. I'm just doing the default two-sided non-equal variance t-test, which is actually also called the Welch's t-test. And if we run that, oh yeah, question says we can do ROC curves in R2. Yeah, I want to get to that next week too. Well, maybe by the end of class, we'll see. But yes, you can do any statistical models you can do in R. Basically, it is a stats language after all. T-test gives us this kind of mess of results. This is the print statement essentially for this Welch's two-sample t-test, which I just performed. It kind of gives us essentially all the stuff we need, but like, how do we even pull this out? We have the p-value, we have the statistic, the degrees of freedom, gives us a confidence interval, gives us the means in each group, which is nice. But this is hard to work with. Like, you're not even gonna really put this in a journal or anything. Like, it's just information. It's not data. I want data out of this. So I'll show you how to pull that out with Broom. But before we get to that, just so you know, reading this like documentation is kind of confusing because it gives you two different options for t-test. One says formula and one says X and Y. And here it's giving you what are X and Y. X is a non-empty numeric vector of data values. Y is an optional numeric vector of data values. And that's because you could do a one sample t-test, but I'm doing a two sample t-test. So I need both X and Y. And I have to, if I'm doing this version, I have to specify my X and Y. And X and Y are going to be the body mass in males and the body mass in females, or vice versa. I did females first. So what I did was actually used poll, which I think Saffron was talking about earlier. And so we have penguins data set. I filtered when sex equals female, and then I used poll to pull out the column as a vector. I don't want a data frame here. I need a vector. And so poll lets me do that pretty easily. I could have also used the $, but I can use poll in like a piping statement. So I just use that for convenience sake. And so that I've put as my X. And I've done the same for males. So I filtered where sex is male and I pulled out male. So let me run this just so you can see what that looks like. So it's this numbers, all these numbers. And here we have the male vector of body masses, same thing. Those are all the male body masses. And then we do the t-test by saying, this is my first column of data. This is our second column of data. And we can see same p-value, same everything. And it gives us all the same information. So that was the same test. I tend to do the test this way, just as a aside, because I like not having to pull out the vectors. This is a lot easier for me, but I did want to show you because that's like the first kind of arguments it gives you. So it's good to know what that means. Way down here, it gives you the formula definition here. And the way I would pull out the information I want, I would again use broom tidy, and I would just save my t-test output as something. So I saved it as my t-test, and then I use broom tidy on that value. And you can see it gives me a tibble. I also did GT. I used GT to make it a little nicer, but an estimate is going to be the estimated difference between and means between the two groups. This is the mean of the first group, mean of the second group, the test statistic, t-test statistic, the p-value, parameters, degrees of freedom, confidence interval of the mean estimate, and then it actually gives you the method and the alternative, which is really nice, just to keep that information for later. In this case, just to show you, glance is actually the same thing. It gives you the same information, and that's because we don't really have this like kind of distinguishing between model parameters and then like a complete summary statistic of the model, like we do in regression. Since the t-test is pretty simple, glance and tidy really just give you the test results, and that's it. So just so you know, not be alarmed that you're not getting something different. It is the same thing. So we'll talk more about all this stuff. I just wanted to introduce statistics because I want to use it with purrr. And so knowing how to do a couple things in statistics land is going to be useful today. But yes, we'll do logistic regression. I'll try to do survival data, and then I'll try to get to prediction, ROC curves, etc. as well. All right. So let's maybe have a break since I keep forgetting to do breaks. So let's come back at 4:17 in like 5 minutes, and then we'll talk about purrr. All right. Let's get back to purrr. So we've talked so far a bit about purrr in terms of how to use map with lists. That's what we talked about all of last time. Just a reminder that there is a purrr cheat sheet on the RStudio website that is very useful and there's cheat sheets for all kinds of things, tidying and dplyr and string R and so on. So those are all really useful references, especially if you're just trying to remember like basic info about what functions are even available. I definitely recommend it. So from the R for Data Science text book. So first, how can you solve the problem for a single element of a list? Once you've solved that problem, then you can take the solution and generalize it across every element in the list. If you're solving a complex problem, purrr will help you break it down into bite-sized pieces. And so then you can kind of put them together with the pipe. So we'll see some examples of that today. And so the purrr structure really is there for iteration. So we used purrr map on lists. Today, we're going to talk a little bit about how to use that with data frames, which I think is a bit more typical usage, at least in terms of data analysis and cleaning. And so first thing we're going to do, the first example we'll see is first, we're going to make a list of file names using list.files. This is just a function in base R that lists all the files in a directory. We saw a little bit last time in the end of class. I used that this kind of problem as a motivation, where we have a list of file names in that folder, and we want to load all of those data frames into a list using map. Then we'll write a function that works on one of those elements, which is going to be a data frame because we've loaded in a list of data frames. And then we're going to use map to apply that function to each element of the list and return a new list. And then if we need to, we will aggregate the final results into one data frame. The second example is going to take a data frame and then make a list out of that data frame, which means kind of chop it up into smaller bits. And then we're going to work on each of those pieces of the data frame. So we'll apply a function that first builds a linear model, and then we will use that linear model and aggregate our results. We'll also show how to write a function that visualizes the data and applies that to each part of the data frame list. So we saw a little bit about functions last time. The idea that if you're going to do something many times, you should write a function. So in this case, we saw this at the end of last class, this function load underscore CSV. And so this is a custom function that reads in a CSV file, and the argument is the path of that CSV file. So the location in your computer or wherever of that CSV file. Then it reads it in. So reads read underscore CSV. So now we've saved it as a data frame, and then uses janitor clean names to clean up the names just in case we need to. And it also adds a column mutate source equals path. You could use mutate or you could use add column here, that they would do the same thing. And then we return that data frame. So what happens if we run this on this path? So there's a data set called clinical.csv in that file, or yeah, in that folder data that we have in this project. And so we can see this has given us a message that it's read in some data. So let's look at my data, which is what I saved it as. So you can see it's read in that file, cleaned up the names, and added this column source, which has the location of that file path. It's the same value for all the rows of this data set. So kind of a simple function, just input a path, output a data frame. But if we have a lot of files, in this case, we have a folder called tumor inside of our data, and it has 4 data sets. So we're going to read in all 4 of those using that function. And we need to know the names of those functions. So the way do we do that to pull out those file names is the function list.files. So list.files, I'll look at the documentation. So list.files, you need to know the path, which is going to give you the directory essentially where you're looking. You can use pattern. You don't have to. In this case, this is the only, if you look back at files, the only function, the only files here are .csv files. So I want to read all of them in, but let's say you had like some extra documentation or something else in here and you only wanted the CSV files. A safe way to do that is to add this argument pattern. And so pattern is going to be a regular expression or string specification that's like essentially like you saw in string detect. It's looking for that string in these file names. So it looked for CSV in these file names and only pulled out the ones that matched that it detected that string. And then I want to use full names.true because that's going to tell that I want the actual path, including the folder data and tumor. So I'll run this and print it out. We can see these are relative to my project. This folder here. This is my project folder because I'm using this part 8.rproj. So it's telling me it's within that folder. It's in the data tumor. And then these are all the file names. So now we have a vector of length 4. It's character vector. And we are going to apply our load underscore CSV function that we created last time up here. So this is our function name, load underscore CSV. And let's just test it. Usually it's a good idea to test that function that you created on something to make sure it's working. So I'm going to test it on this first one. I'll just show you with that. Speaking of indexing and seeing some examples, when we have a vector and we just want to pull out the first one, we use the bracket, single bracket, because it's a vector, and single bracket pulls out the first element. And that is that LUSC data set. And so if we run load CSV on that argument, we end up with one data frame, a tibble, rows 504, 43 columns. If you look, you can kind of see, essentially there's a disease column. Can you miss it? Source. Yeah, so there's the source, which it was added by the function, which tells us the column. There's the column that tells us the file name. Disease, these are separated out by disease. So this is the LUSC disease, and that is the lung samples are all here, and that tells us that in that column as well. So that seems to have worked. It looks good. But so how would we do that for all 4 of those files here? And so that's where purrr comes in. I've added this screenshot from the cheat sheet because I liked how it visualized it. So map, if you remember, the way we use map is we put the list first, then we put our function, and then we put any arguments to that function. And what that does is it applies function to each element of those lists, function, 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 and returns a list of new stuff. So we have a 3 list here with whatever the result was from that function. This is a reminder, the arguments are first are your list name, second is the function to apply. And so the function we're applying is load underscore CSV, and the list is files to load. So a side note is that files to load is not actually a list, it's a character vector. We can check that by saying class files to load. That tells me character. You can also just kind of look at it, and that is a vector. So purrr map, last time we used it only on lists, but it actually will work on vectors or data frames. I'm just going to focus on lists and vectors for now, because for data frames, I don't really use it that way. We have other ways of iterating over the columns of our data frame. But for lists and vectors, I think of those as kind of similar ideas in that they contain elements that I want to iterate over. So in this case, all of our elements are the same type. They're just characters, strings. And so we have 4 of them. And so whether it's a list or a vector doesn't really matter here. But if we did want to change it to a list, the as.list function will do that for us. So look at the regular output. This is the regular vector. This is what a vector output looks like. Once we convert it to a list, this is what the list output looks like. It separated it into the number 1 element, 2 element, 3 element, and 4 element. And then I could say, what's the class of that thing? It's a list. So we know that that is now a list, but we don't need to do this. I'm just showing you just in case you ever see that code, that's what it's doing. And just as a reminder, for object types, a vector, because now that we have this one more, the list might be adding some confusion. So a vector, which we learned in the very beginning, is an object type where every element must have the same type. So if you have character strings, you're going to have a character vector. If you have numeric values, you're going to have a numeric vector. You have a Boolean, you're going to have a true false Boolean vector, and so on. A data frame is an object type where each element column can be a different type, but within that element, which is a column, the values must be the same type, and all columns must have the same length. That is another restriction. So we're going to see in a bit that you can have what's called a list column. That is a column that contains lists, and that is a little funky, but it is useful. And then the last type of object that we're talking about is list, and that's an object type where every element can be different, a different type, a different length, a different everything. So just for examples, these would be how we would make vectors, usually with concatenate. This, just so you can see another one, numeric 2, this is also a vector, right? So that's another shorthand way of counting from 1 to 100. All of these are vectors. A data frame we can create with the function tibble, because tibble is a data frame. Everything needs to be the same length. So here I've created a column, city, size, area. Each of those have 2 rows. So I'll just run that so you can see what it does. Data frame, 2 rows, 3 columns. If I had tried to put another element in here, it gives me an error because they are not all the same length. So that is not allowed. But a list, I could do basically whatever I want. Here, I tried to put a list inside a list, which is allowed. My first element is another list with length 2. My second element is a numeric value, a numeric vector. And my third element is actually the result from my model. So here, X list, if I print it, is this kind of mess of information, but it is, if we ask, what is this? It's a list, but it has value, which is this first element is the value, second element is key, and the third element is model out. So you could pull out each one of those elements if you wanted, but list is just super flexible. So that's how it's different from all these other data types. Any questions about that? Okay. Okay, back to map. So we're going to put our vector of files on the left. So that's our first argument. And then here is our function. And we're going to run map on that input. And so what it's done, it's giving me messages. This is just information. It's not data, but it's giving me the print messages when I load in data from read_CSV. And it's showing me I've read in 4 data frames. And if we look at file list, it's kind of different how it prints out in interactive versus when you knit it, but you can see there are 4 data sets. It's showing me them in tabs, but if I had knitted this, it would show them in like kind of stacked on top of each other. Actually, what happens if I put it here? You kind of see it here. So when I put it in the console, it's showing me that typical list output where it has 1, and then it puts like a little bit about the tibble, 2 is another tibble, 3 is another tibble, 4 is another tibble. So when you're working in an RMD, it tries to make it a little cleaner, but that can also be confusing. Oh, now I lost my, here it is. One thing to note though is that it's numbering them 1, 2, 3, 4. It doesn't have names. And so to give it names, we can use the names function and then just give it the files to load vector as the names. So what happens when we do that? I'll put it over here and I'm typing in the console so you can see. See, this is the 4th element now has become the name of it is data tumor read CSV. And it has to put these little backticks here because of the backslashes or the forward slashes, doesn't like that, but you are allowed to name it something like that. And the reason we name our lists is because when we run map, we get the names back. So it gives us some information that can be useful. So I actually answered all this for you. So what is the output of per map? It is a list. You can say class to figure out if it's a list. That tells you, oh, no, not list, file list, list. Or you could say structure, str. That gives you kind of a lot of information. I don't like to do that on lists because it's really hard to see. But if you look at the top of structure, it gives you list of 4. So you do get that nice information out, but otherwise that's a whole mess. So class is usually what I use to check, but you are getting a list out and we've named it. This is the same thing that I forgot to delete. So as an aside, we used map on a vector and then we named the resulting list. We could have named the list originally and then have done map. So if you look back at our files to load, these are the 4 files we read in: lusc.csv, meso.csv, prod.csv, read.csv. I could have named this vector. So we saw today in the function of the week, a named vector when you use poll on 2 variables, which I didn't realize it did, but that is pretty handy. I can name any vector as long as I give it the right number of names. There's 4 elements. I'll just name it so you can see. What does it look like now? So you can see how it's done this like paired printing where it's telling me it's still a vector, it still has no dimensions. It just has a length of length 4, but each element has its own name. So LUSC, MESO, Prad, Read, these are the names of those elements. So similar to having a named list where each of the slots or elements in our list are named, here each of the slots or elements in our vector are named. And so now that this vector is named and we run purrr on it, we can actually end up with the names in the resulting list. So we've ended up with those same names. So I'll put it over here in the console to see that the way that it prints the list. You can see, scroll up, file list 2 has names LUSC, MESO, PRAD, and READ. So that can be handy if you want to name it by hand like that, just so you know that's an option. And then just to show a little bit more examples with the bracketing. So when we want to pull out one element from a list and have it be the type of element that is contained in that element. So for example, if I want to pull out, let's say read data frame, the way I would do that is with the double brackets. So here I'm pulling out the first element with double brackets. I'll just put that first. So we can see it's pulling out a tibble, and we can actually run functions on that. We can see the dimensions is 504, 403. That's 43 columns, 504 rows. The class is a tibble data frame. Lots of different classes, but deep down it's a data frame. But if we had done just the one bracket, so if we only use one bracket, it's actually going to return a list. If we look at that, this little $ showed up first. I'll put it in the console so you can see it a little bit easier. This is what the output is, all of this. It tells me the name of the list because it's a list of length 1. And then it shows me that there's a tibble inside that element. And so if I try to get the dimensions of this, this is not going to work. It's going to be null because it's a list and the list doesn't have dimensions. If I try to say names of that, for instance, maybe another one, we just get that name of that one list element. We're not getting the column names. Actually, I don't even think column names would run. Yeah, no. So it's not a tibble, it's a list. And we can check that by running class of that thing. That one bracketed accessor is a list of length 1. So length file list 1 is 1. And then if I try to do length file list double bracket 1, it's 43 is going to give me the number of columns. So just keep in mind what you're getting out. The homework talks about this as well, what you get out with a double bracket versus a bracket. It's easy to check what it is and just kind of be aware of what you're pulling when you're doing that. All right, so how do we combine our results? We have mapped our file names and we've pulled out the data that's contained in those files. And then we have a list that has 4 tibbles in it. I showed you last time that you can actually just bind rows on a list. That works. And so if we did that, and then we glimpsed it, we would end up with same number of columns, but it's stacked them on top of each other because it's done a row bind. And so now we have 1,263 rows. And we can see if we look at the sources from that full data set, we have all 4 files. We've gotten these number of rows from each of those files. So that seemed to work well. Last time I used bind rows, but I included a .id argument to kind of give a source name, but we already have this column source. So we don't actually really need to do that here because we already have from that function, it's added this source column. So I already kind of have an identifier of what data that came from. There's another function inside purrr called reduce. I actually don't use reduce that often, but it can be useful in certain situations. And it's more general than bind rows. So what reduce does is it kind of what it sounds like. It reduces your list into one thing. And the way it does that is it applies this function, whatever function you tell it, for example, bind rows or sum or join, and it applies that function recursively to each element. So first it does it for the first two, A and B in this case, and then that result gets put into the first argument, and then it joins or binds or whatever the function is with C. And then again, it gets put into the first argument, and then it binds it with D. And so the difference between map and reduce is what it returns. So map returns a list or a data structure with the same number inputs as same number elements as its input. And the reduce is to take, the goal is to take that list and return one object. So the way we would recreate this bind rows code, which was, I admit, a lot simpler, is to use reduce on that file list. So that's the list of the data frames, and use bind rows as my function. And so this is doing the exact same thing. The list first and then the function second. We end up with the same number of rows, same number of columns. It's all it's done is bind rows, the first and second element, put them together, then bound rows with the third element and put them together, then bound rows with the fourth element and put them together. And then you end up with all of them stacked on top of each other. So obviously it's not that useful to use bind rows because you could just have used straight up bind rows. But, and this is just showing you that it's the same thing, but using other functions can be useful. So for example, in this kind of mini challenge, what we first want to do is say, take my file list and count up the number of rows. So I'm going to create here, I'm creating a list of number of rows of each data frame. And so then I'll end up with a list that has 4 elements, and it will have 4 numbers, however many number of rows in each of those data sets. And then I will use reduce to add up the rows, the number of rows. So if we think about it, what's the function that we're applying to our file list? This is, if you remember what file list is, it's the 4 data sets. So to pull out the number of rows on the 4 data sets, you would use the function nrow. So that's exactly what we would put here. And we can look at that. Paste it here so you can see. We have 4 elements again, because whenever we use map, we end up with the same number of elements that we started with. And it has summarized it by giving me just the number of rows. So what reduce is going to do is going to add these 2 numbers, 504 plus 87. And then whatever that sum is, we'll add it to 500. And then whatever that sum is, it will add it to 172. And so we can put sum here, and that will do precisely what I was just describing. And it will give us the same number of rows as that like stacked data set where we bound the rows together. So this is a kind of a very simplistic way to use reduce. I would think that the most common way to use reduce is actually with join. It doesn't make sense to join, to like left join or full join those 4 data sets because they're not on the same patients. But if you had 4, 10, 50 data sets that all were on the same subjects or same patients or same observation IDs, for example, and you maybe want to join them all together, reduce would be very useful in that situation. So I couldn't think of like a very complex example, but this is a very simple example how you would do that from the R for Data Science book. So I've here I copied them. They created a list of 3 tibbles. So pretend that this is actually a big data set, but this is a very simple example. So it's just a tiny data set where we have one person, John, and we have their age. Here we have 2 people, John and Mary, and we have their sex. And that's the 3rd tibble, or 2nd tibble. And the 3rd tibble, we have one person, Mary, and we have their treatment. And so we have the same people in these 3 tibbles, but different data elements. So we have age, sex, and treatment, and they're all in different data frames. And so this is sort of common where you have Like say the lab gives you some data, and then you have the demographic data in one, and you have measurements from some survey in another, and you want to join them all together. So you could create the list of data frames by reading them all in using map, and then you can use reduce with full join. So reduce would have your list on the left as your first argument, and then you'd have the function as your second argument. The same way that we could run that is with a pipe, because dfs is your first argument, and then you would pipe on reduce. So take your list and then reduce using full join. Most of these like map and reduce and map2 and all the other purrr functions can be piped like this, because you just put your first argument here before the pipe. So these do the same thing, just so you see it written different ways. So let's run this. So what we have, reduce has first full joined these two data sets. So it's put age and sex together. And then on that tibble, it's taken that tibble, this joined tibble, and joined it, full joined it with treatment. So it's added on the treatment column. So now we have all three measurements, age, sex, treatment, and all of the people that were in the data together. So very simplistic example, but you can imagine if you had data like this, doing full join on all of them would be a lot faster than doing each one individually. And of course, always be careful that it's doing what you want it to do. All right, any questions about map before we talk about other map? Extra maps. All right. Well, so far we've just been using regular, as I call it, plain vanilla map. Just map takes a list or a vector, as you've seen, and returns a list. Map always returns a list. But if you are running a function and you know that it's going to output, say, one number or one data frame or one character, etc., you know the type of object that your function is returning, and you know that you want to combine them together either in one vector or one list, or sorry, one vector or one data frame, etc., then you would use what we call a type specific map, just to skip essentially the reducing or the bind rows or the concatenate or whatever you're trying to do. So there are type specific maps that are written like this. So map underscore int, map underscore LGL, these are telling you what the output should be. So map int returns an integer vector. Your map LGL is saying that your function should return a logical vector. This map double, it should return a double or numeric or decimal vector. And then map DFR, DFC should return a data frame. The main difference between these is that they are very strict in that if your function doesn't return the desired data type, it will return an error. And you will probably see that many times. It's very easy to kind of mess these up that way. This is a table from the cheat sheet that I liked because it has kind of all of them written out next to each other. Today we're going to talk about map DFR the most, but there are kind of the character vector or integer vector ones can also be, or not integer, but I don't usually use integers. Double, I'd say, is more commonly used. So numeric, character, data frame. So in the example that we did above, we loaded data frames. We know that the output is going to be a data frame. And so we would expect a list of data frames as an output of map. But because we know that we're outputting data frames and we want to bind them all together row-wise, what we would use is the function map DFR to return one long data frame. So this was how we used map. Function map takes the files to load list and then the function that we're applying. Map DF is the exact same thing. Actually, I'm going to use DFR. DF and DFR are the same. So here, just for clarity, this is the row-wise stacking. So map DFR is going to take your data frames and row bind them. Map DFC will take your data frames and column bind them. It's much less common to column bind because you need the exact same number of rows and you need to know that that makes sense. They're like in the right order. I'd say it's pretty rare that you're going to use DFC. DFR is going to be more useful almost all the time. So let's run that just so you can see. Glimpse file DF is my output. It is one big table, that same 1263 row table that has all of them stacked on top of each other. So that is nice. I didn't have to do map and then bind rows or map and then reduce. It just does it all in one go. And so that is skipping a step basically. So the DFR part corresponds, like I was saying, data frame rows, which means the data frames were combined through row binding. DFC is the data frame created by column binding. And so this is from the map documentation. They're all in there together. So it tries to tease them out for you. So you get your map always returns a list. These logical integer double character return a vector. Data frames contain a data frame. One thing to note though is that the return value of your function must be length 1 for each element of .x. So .x is your list, .f is your function. So you can't return like multiple things from your function. You can't return a vector or a list. It can only be one thing, one length 1. So it has to be a vector of length 1 or a list of length or a data frame, one data frame. So for example, above we calculated the n row. So let's do that again. If we run map on that file list calculating n row and we look at the results, we get a list just like we did this above, the list of all the row numbers. And if we look at the class, it's a list just as we would expect. But if we look at that list, it's a list where each element is one number. So that's a clue that we could use map double to return a numeric vector, basically converting this into a vector instead of a list. So if we do that with map double, it's the exact same format of the way we used map. And now we look at that result, it's a vector. It's actually a named vector again, because we have these the list names now are the vector names. And if we look at the class, it's saying numeric, which means it's a numeric vector. So that's kind of a simple way to use that map double. So like I said, you have to be careful about your function. It can only return one thing, one thing that has length 1. So another function that is useful is dim. Dim is the dimensions of your data. It's 504 rows, 43 columns. This is a vector of length 2. If we run map on this, say I want to take the dim, get the dimensions of all my files, that works great. We have a list of length 4. Each element is a vector of length 2, but if I tried to run map double on that, it's going to complain. Stop bad type. It's just kind of a scary error, I guess. Result 1 must be a single double, not an integer vector of length 2. So it's scolding me for not having a function that returns length 1. And so I would say oftentimes when I'm using, I know I want to try to use map double or something like that, I will often run map first and make sure it works the way I want it to, and then change it to map double or map DFC or DFR or whatever, because I've gotten this error many times. It's easy to do. And as we'll see, if we get to it today, if this function fails on one of your elements, like say you get an error on one of your elements, it will kind of create a mess for you. So we'll talk about how to deal with that later, but for now, map is kind of my default. And then sometimes for simplicity, I'll say, oh, I could just change that to map double, it'll make my life easier. I'll do that because I know it works. So that was this part. The return values of our function must be of length 1 for each element of X. And another example, a little bit contrived example, but it is kind of a case study of things that you might do with your data frame. So suppose we have our 4 disease data sets, our tumor data sets, and I want to make a cross table of tumor status by vital status. So the way I would do this for each of my data sets, I would create a function to do the work that I want. In this case, I will create a function that inputs the data frame and then uses table on that data frame. So data frame pipe table. And then I name the 2 columns I want to make a cross table of. An aside that is related to your homework in a sense, that last week's homework. I mentioned this last time, but I haven't shown you yet how to pass column names as an argument. It's actually quite tricky. For example, what I mean here is you might imagine that a more useful function would be something like this, var1, var2. And then I could say var1, var2. And so I would use a function where I would say, here's my data, here's the 2 values I want to make a table out of. This won't work because var1 you're going to pass as a character vector. And these pipeable functions take what I call like the bare column names. They don't take the quoted column names. And so we'll talk about this probably next week. I meant to put it in this week's, but I ran out of time. And then that's called tidy eval. So we need tidy eval to get this kind of thing to work. So anything like summarize, mutate, select, all that stuff, this won't work. So don't try to do that for your homework. You have to actually what I call hard code your variable names for now until I show you how to do it the other way. So we're a bit restricted in what we can do right now. But I do want to, let's say I really want to make a table out of tumor stage and vital status. So what I would do is take that table and then return my result, cross table, I'm calling it. So this is my function. And then I test it out on the first element of my file list just to make sure it works. And so I can see it did make a table of tumor stage and vital status. That looks great. So what is that? It's actually a data frame because it is the result of the table function. The table function makes a data frame. And so that's what's being outputted from that function. So if we run it on all the elements of our list, we use map. There's our list and there's our function. And so we can see our out list, which is the result of map, is a list, 4 elements, same names, and it's the table with a Y of vital status and tumor stage. You can see, for example, in this data set, the only tumor stage in that data set is not reported. And then all this, like this one has all kinds of tumor stages and missing. So you get a sense of what's in that data. But because I know each of these is a data frame, I could use map DFR, and that's going to take all these 4 and bind rows them. So it's going to make one long data frame. And in this case, I do want to say ID equals .id equals source. So this is an argument of map, and it's also an argument of all these other type specific maps. And that's saying I'm going to take the name of my list element, and add a column that's called source, and it puts that name along all of the rows in that data frame. So this one, Prad CSV, is only going to have 1 row. This one is going to have many rows. This one's going to have 6 rows, and it's going to say meso.csv all along those rows. And so we can see what that looks like. Here is the full data set. So we have the LUSC data, cross table, meso, prad, it's only that 2, or 1, sorry, and then read, READ is all of that. Just to show you again, GT is nice to make tables. It's nice when you have, like a grouping. So if let me just run it regular GT. So GT with no arguments gives me just an HTML table. Oops. An HTML table of what you just saw. You can see that source is duplicated across all those rows. If you have something like this where you think of this as a subtable and it's defined by source, so LUSC table is this section, and you want to kind of make sections in your table. MESO is this cross table, PRAD is that one, and READ is that subtable. You can specify the group name column argument in GT, and you tell it the column name. In this case, it was called source. And what that does is it turns that into a grouping instead of actually a column. So you can see the LUSC data is now kind of has this little header and is separated out. So here's that. Then the MESO data cross table is here, PRAD is there, READ is there. So that can be useful for visualizing summary statistics and so on. This is kind of a very specific use case, but this is this kind of workflow is pretty useful if you have multiple data frames you're summarizing across. Okay, so now finally we have a challenge after all that. There's not that many of you, but let's see. I think maybe we could just do like 2 groups and kind of work together if you can to do 2 different things. So write a function first, that simple function returns the first column of a data frame. Input a data frame, return the column, first column name. And then use whatever type specific map function that makes sense to apply that to that file list and return a vector. And the second task is to write a function that takes a data frame as an argument and returns the first 3 rows. This actually hint should probably just be up here. Hint, there's many functions that do that. You could use slice or head or slice underscore head. And then you use map to apply that to that file list and return a stacked row-wise data frame. And then just for practice, you can use select or relocate, which you learned, I think, last week, on the data frame to move that source column to the front, the first column, so you can see it a little easier. Well, you made some headway. I'm going to attempt to solve this in real time. It may be a disaster. We will see how it goes. Okay, so the first thing I want to do is return a function or create a function that returns the first column name of a data frame. The way I would return the first column of a data frame, let's just use penguins, is to probably just do call names penguins 1. Simple way to do it. I'm sure there's you could do other ways. I could select just one of them and then take the call names of that. Either way. So what I would do here is create a function. I think originally called it, say, first call function data frame. And then that is precisely what I want to return, but I want to do it for a general data frame. And so this would be my function. I could, to be safe, put that inside return. So run that, double check that it works. Let's do on penguins. And that gives me species. Okay. But I want to apply that function to each of the elements of file list. So I'm going to map file list, first call. And what does that look like? That gives me a list. But what this is asking is a vector. And so all of these are characters. So I can use map character. And then I would end up with a vector of the first columns. And I would have all 4 of them in one vector, not a list. So that's how you would do part 1. Any questions about that? I lost my chat. And for part 2, so it says, write a function that takes a data frame as an argument and returns the first 3 rows. So let's just try penguins again. How would we return the first 3 rows? You could use head or slice. Or slice head. I'd like to use slice just because I know what it's doing. And that's giving me rows 1 through 3. And so to write a function like that, first, let's call it first 3 rows function, df. This would be my data frame. And then I would return that. Actually, you can also pipe return at the end if you really wanted to do that. I don't know which way looks cleaner, but that is a possibility. So that's going to return the first 3 rows of that data frame. Let's just double check that it works on penguins. That looks good. So I want to map on file list that function, first 3 rows. That's going to give me a list of 4 data frames of row number of dimension 3 times however many columns. But I want to actually make one long data frame. So dfr gives us the one long data frame list. And so now I can see if I scroll over, eventually, at the end, there's that source column, and I can see that those are all 3 of my data frames. But what I asked you to do in this last one is to use either select or relocate to put source at the beginning. So relocate source will give you the same data frame, but source has been moved to the first, first place, first column. If you wanted to do that with select, I would do select source and then everything is the function to pull out every other column. But relocate's a little simpler. All right. Any questions about that? Okay. So the next section is a whole other kind of workflow. Yeah, I think we'll get through a lot of this, I think. So the idea here is that we're going to use map on a different kind of list. So here, so far, we've been able to apply a function to a list of data frames, for example, or a list of other stuff. But there's not that many real life scenarios where you would just be handed a list of data frames. Sure, if you have like 10 files that you're reading in, that makes sense. But probably you're creating your list to run a function across. And so the way that we most of the time, or at least I most of the time use map, is if I start out with a data frame and I want to split it into sub data frames or apply a function across sections of that data, for example. So the idea here is we start with one data frame, subdivide it into a list of data frames, and then we can use map. So let's think about going back, let's go back to the penguins data set. We have those 3 species, Gentoo, Adelaide, and Chinstrap. We could split penguins up into 3 lists where the first, or sorry, a list of length 3, where the first element has only data from the Gentoo penguins, the second only from the Adelaide, the third only from the Chinstrap, for example. And then we can apply map. So for our examples, we're going to use map to first make a plot for each of those data sets. So 3 different plots. And then we're going to use map to run a linear model for each slot. So 3 different linear models, essentially like a stratified analysis. There are actually a lot of different ways to do something like this. I thought of three different ways that I could think of that I think are used pretty commonly. And so the first that we're going to talk about is using group by. So we learned group by way back when we talked about summarize, mostly when we were summarizing data sets. And then we'll use a new function called group split. And that will create a list of 3 data frames corresponding to our grouping variable, which in this case is species. Then we'll have a list. And so we can use map on that list to apply our functions that we create. The second way is to use a function called group nest. And nest, which we'll talk about, means that we're creating a nested data set that has a column that is a list column that contains the subset data. And we'll see that, what all that means. Those are all newfangled words. We'll talk about that. Once we have that, we can then use mutate on that column and then essentially use map that way. The other way is to use group map. I am only going to talk about the first two ways. I think group map is probably easy to follow after you understand the first two ways, so I'm not going to get into it, but it is also a kind of, it's actually kind of a simpler way to do things. But you really need to understand what's going on behind the scenes. So that's why I decided to focus on these two, just to kind of spell it out for you. I tend to use this group nest method, as I'll talk about later. But it's really a matter of preference. Once you see these methods and which way you find that makes more sense or is a little cleaner, it's up to you. They both can be used in similar ways. So the first way is chopping up a data frame by group using group split. There's a base R function called split also that works, but the tidyverse kind of way to incorporate groups, there is a function group _ split, and that's what we're going to use. So how does this differ from group by? So we saw group by, which doesn't actually change anything really explicitly about the data, I should say, when we apply group by. So let's look at what happens with penguins. Penguins group by species. So I'm going to make penguins grouped. That in itself, all that has done, if we just look at penguins grouped, is added this extra piece of information. It's really the same data. It's a data frame. All the essential information is the same. Nothing has changed other than this kind of extra information, which we can think of as like another attribute of our data frame, is that it's grouped. And there are 3 species. That's what it's telling me: Adelaide, Gentoo, Chinstrap, or whatever the third one was. And those are the groups. By itself, grouped by is not that useful. We've seen it in conjunction with summarize to make summarized tables by group. In this case, we're going to use that grouped data set to split it. So let's look at this. We're going to split this data frame into 3 data frames, a list of 3 data frames defined by that species, which is the grouping variable. Keep.true, keep equals true, keeps that information. It keeps the species column in the data set. So it's splitting it into 3 data sets, and each of them still has that species column. By default, it gets rid of that grouping column, but I want to keep that information. So let's do that. Penguins grouped and then group split. And I'm going to say that as penguins by species. So what is penguins by species? If I print it out, the first thing it tells me is it's a list. This is some information. There are 3 slots. This is the first slot, second slot, third slot. If I ask what kind of class, like what object is this? It gives us some extra stuff. This is a special kind of list. We don't need to worry about that, but we do need to realize that it is a list. It's that type of object. How many elements are in this list? We can say length of that list is 3. Does the list have names? Is it a named list? No, it has not been given any names. The thing about this method that I find confusing and I don't particularly like is this whole naming situation. In order to get the names out, we have to use another function called group keys. So we have this list. It is what we want it to be, but it doesn't have some informative names. And in order to get those, this table, grouped keys, penguins groups, has that naming information. So this should be the first name because that's the first species. This should be the second name, and this should be the third name. And so again, I'm going to use pull to pull out that vector. If I used select, it would still be a data frame, and I need it to be a vector. So that's why I used pull. And then that is going to be saved as my species names. So let's look at what that is. Just a 3. It's actually not a character vector. It's actually a factor. That part doesn't really matter. But it is of length 3. We have a list of 3 elements that all matches up, which means I can name that original list, which is the output from up here, the split it up list, I can give that list the names, species names. So now if I print that out, I can see it's telling me the names here. I really don't like how, I mean, it's nice that the Markdown gives you a nicely printed table, but it's hard to see for lists. So I'm putting it in the console so you can really see. This is my penguins by species. I've added these names. This extra stuff has to do with that special kind of list. You can kind of ignore it. It's just telling me what the variable types are of my data sets that have been split up, but it's just extra information. It's trying to help me, but I don't really need that right now. So we can see Adelaide is the first element of our list. Chin strap is the second element. Gen 2 is the third element. So now we have a list of 3 data sets. So previously we got our list of data sets by reading in 3 files. Now I've just created a list of data sets by splitting up original data set by group. Okay, so what do we want to do with this data? I said I wanted to make a plot and I wanted to run a model. So for example, it's bigger. I'm gonna build a scatter plot where I plot bill depth versus bill length. Geom point is a scatter plot. And then I'm also gonna add a smoothing line. The linear smoothing line is method equals LM. And I'm going to give it a title. And I want the title to be species. So the way I pull out species from that data frame input is I know that every column or every data has a species column. Chinstrap does, and that was because I said keep equals true. I kept that grouping variable. And so I know it's all the same. It's going to be the same in each data frame. So I'm just going to take the first one just to like pull out that information from the data frame. I can get the name of the species that way. And that's what I'm making my title. So just ggplot code to make a scatter plot, geom smooth, and add a label, the title. And so that's my function, build scatter plot. It takes a data frame. I'm going to test it on the first, well, not the first, the second element, I guess, the element named Gen 2. So if I run this, it did what I thought it was going to do, which is make a scatter plot with a line, smoothing line. And build depth is on the x-axis, build length is on the y-axis. Here is my title, Gen 2. I can't highlight it, but up here. So that's great. But now I want to make 3 plots. I want to make one for each species. And so that's where map comes in. I have my list. So this is my first argument is the list name. And then I have my function name, map list function. Function is the scatter plot function. And I'm going to save that list output as plot underscore list. And then if I call that, it prints out a list of 3 plots. Let me see if I can show you. It's hard to see what this really is. Well, I have a lot of stuff. What did I call it? Plot list. Plot list. If I try to view it, actually I could have just done, I could have just done view plot list. R shows me it's a list of length 3. And within that is a ggplot. So this is a different type of object. It's technically a list because the ggplot object is a list, but this is telling me the class of that object is a ggplot. It's gonna have a lot of information all about the plot and everything. But when we call its name, which is calling the print statement for that object type, it's printing the ggplot, like the visual plot. So that's exactly what we wanted. It's a nice way to easily make 3 essentially identical plots, but with 3 different sub data sets defined by species. And so the other thing I wanted to do, the other type of function was build a model. So let's do the same kind of thing, but for a linear model. We want to model bill length as a function of bill depth. So bill length is our outcome, bill depth is our predictor. And so the way, just to show you how I would probably do this, is I would first try to write this with just one data frame. So I'm just going to make my little mini Gen 2 data frame just to make sure it works. I could have also have done, what's the name of my thing? Penguins by species. It's the same, Gen 2. These are the same data sets. This is me filtering. This is me pulling out from that list. Either way, I would just want to make sure that I can write the code to work for one data frame, and then I make a function out of that. So I want to pull out the species info again, get my species, take that first element. So that should be Gen 2. Then I'm going to fit a model. So this is my model code, LM. This is my outcome. This is my predictor. I also threw in sex in there just so we can have 2, so you can see what that looks like. And then I need to specify my data, which I call DF. I also want to tidy up the model results. So I'm going to use broom tidy. I'm going to ask for the confidence interval. And so this is essentially the code I want in my function. Pull out the species, and build the model, make the tidy function. So the result I want to print out is the result from my tidying, this part. I want to add the column that has the species so I can see what species I'm analyzing. And then I'm going to relocate species so it's at the front of the list, so at the beginning of our columns. And I want to return this data. So I'm just going to run all this code to show you what the output looks like. Here is our tidy, broom tidied data model results, p-value, confidence intervals, etc. We have the terms, build depth, and sex. Build depth is a continuous variable, so we get an estimate of for every 1 unit increase, or for every 1 millimeter increase, we'd expect that the length would increase by 1.3 millimeters. That's how you would interpret that. And this species column tells me I've just looked at the Gen 2 data. So that's the code that I'm going to generalize in my function. So my function I'm going to call run_model. I'm going to use data frame df as my input. Again, same thing. I pull out the species. I run the model, same way. I pull out my out results. This is the exact same code as above. And then I return that data frame. And I can test that function on one element of my list, which is this, again, the Gen 2 data. So I should get the same thing, and I do get the same result as that code above. So now I have a function called run model, and I'm going to run model. I'm going to map run my model across the 3 species lists, subdata sets. So map, name of my list, name of my function. And again, we have a list of length 3. It's 3 data frames. If we use view more often, if we look view, you can see a list of length 3. Adelaide is a data frame. You can see Tibble DF, Tibble with 3 rows and 8 columns. So we're getting that output for all 3 of our species. But because we know all 3 of them are data frames, we could have actually used map DFR. And so what does that look like? Now we have them bound together into one long stacked data set. We have Adelaide, Chinstrap, Gen 2. And so this is kind of nice if you want to compare the build depth estimates across species, or how different is that association. So right now, it's kind of just a big table of numbers. I could, for instance, filter term equals, let's just look at sex actually, it's a little easier. We can see that if we look at sex differences, it's actually very similar across species. 2 to 3 is the effect size, which means we'd expect an increase of approximately 2 to 3 grams comparing male and females on average. And the p-values are significant for all 3, confidence intervals, and so on. So you can see that. I did want to throw in another ggplot geom that we haven't seen before. So if you have done any kind of stats or epi analyses, you probably have seen what are called forest plots, which show an estimate from either a regression model or maybe some other way of calculating an odds ratio or a hazards ratio, some sort of statistic, along with the corresponding confidence interval. So it's like a visualization of this table with the estimate and the confidence interval. The way you would make that in ggplot is with the geometry geom_error bar to show the bars, and then geom point to show the point estimate. So we've seen geom point before. That's how we made scatter plots. We know that it takes an x for an x-axis value or y for a y-axis value. And there are other kind of customization mappings like color, which we've used, shape, size, alpha. Those are ways to show groupings, essentially, usually. And then geom error bar takes another aesthetic. It takes x min and x max, or y min and y max, depending on whether you're making a horizontal versus vertical bar. So you'll see that here. So if you want a horizontal error bar, like left to right, you use x min and x max. And if you want vertical, you would use y min and y max. So I'm using x here. First, I'm going to pull out the coefficient data just to make it a little cleaner. So I'm taking out the intercept and I'm changing the names of my terms. So if I look up here, the term sex male is sort of an awkward statement. So I've changed that to male versus female. The other term was bill depth. I've changed that to just a nicer way of calling it. So let me just run this part so you can see. Coefficient data is now term has been made nicer. And I got rid of the intercept term because I don't want to plot that. So I'm going to plot the estimate and the confidence interval for each of these rows. I also want to specify which one came from which species. So this will make more sense when you see the plot, I think. Let me just show you. So I'm using that data that it is made, and then my aesthetic, I put them all together. I want my y-axis to be species, so that means I'm grouping my bars by species. I want my x-axis to be the estimate. That's going to tell me where my point is. And then I want my error bars to be defined by the confidence interval. And then I'm going to color it by species just to make it look a little nicer. If I just do geom point, so I'm only running here this far, what plot does that make? We can see the estimate, which is our coefficient estimate on the x-axis, the species on the y-axis, and they each have 2, and that's because there's 2 terms. I haven't done anything with terms, so it's not telling me which one's the sex estimate, which one's the whatever it was, bill depth. Bill depth? Yeah, bill depth. If I add error bar, I'm just running this part of the code plus the error bar. Now we can see the error bars, but they're all lined up on top of each other. And I, again, don't know which one is term. So in order to specify that, I use facet. And I'm going to use facet wrap here, faceting on term, which is which coefficient estimate or which predictor I'm looking at. I'm going to make scales free X because, as you'll see, the scales are quite different. So for this is bill depth, it's going from around 0 to 2, whereas male versus female had a much larger effect size. And so the scale was allowed to vary on the x-axis and went between 1 to 4. The rest of this stuff is just making it look nicer. So I add a vertical line at 0 to show the null value, which would mean no effect. I changed the theme, I changed the color, I got rid of this legend because we don't really need it. It's obvious what colors are by the y-axis. And then I added some x-axis labels, etc. I added a title, just make it look a little better. So all those extra customizations, there's my vertical line. I changed the color to be the colorblind scale. I changed my x-axis, I changed my y-axis, and then the facets are here already. Here's my title and my subtitle. So this is what a forest plot looks like. You've probably seen them if you've done any kind of like meta-analysis or anything where you're comparing estimates across either data sets or stratified data. It's just a visualization of that confidence interval, really. The other way people use error bars, probably if you're in basic science, you've probably seen this a lot where they do bar charts and put the little errors on top of the bars. That's another way to use it. So I think that's just a nice visualization of our results. And we got that from mapping across the 3 species. So we have estimates for all 3 sub-data sets, which is nice. Let's see. I think we have time for this. Maybe let's have like a 3-minute break just to gather our thoughts, and we'll come back at like 5:43-ish for the next round. One thing I just saw is this warning. So this is a good reminder that I wanted to mention that especially purrr, but also ggpubr and other tidyverse stuff, it's like they're always changing things. This is telling me that guides scale equals false. So I used guides color equals false because that's the way that I learned how to do it, is deprecated. That means that they're not using that method anymore. They're telling me to use guides scale equals none instead. So I need to remember that because I did not know that. So just keep that in mind when you're looking at old lessons, like even some of the readings that I've given you for the readings for the class, they're pretty old and things have changed and some of them have not been updated. So keep that in mind. Sometimes if you try something from the internet and it doesn't work, it's probably because they changed something up on us. So kind of annoying, but I think the end goal is that they're just trying to make it all more streamlined and consistent and everything. So that means that some things are going to break. And deprecated is a nice way of saying it still works for now, but if you keep using it in 6 months, it'll probably be completely broken. So hurry up and change your ways. That's what they're saying. Okay. Actually, let me look at my list of other things to mention. Okay, that was it. So the next thing I want to talk about is group nest. So that first way that I talked about using map on a data frame chopped up into bits was using group split to make a list. Here, I'm going to use group nest to make a list column. So to use this method, we first need to understand what are list columns and then what it means to nest a data frame. A list column is what it sounds like, a column in a data frame that contains lists. We have seen data frames that have vectors of different types, like character, numeric, vector, logical. It's the same idea, except each element of the column is actually a list. So here is how you would make a very simple list column. Here I'm making a data frame. Remember, a data frame has to have the same number of rows. So in this case, patient ID is a numeric vector of length 3, date is a character vector of length 3, and list call is a list of length 3. So the list has to have the same number of what we think of as rows or elements as everything else in the data frame. So what does that look like? This is like the printing that it gives me. It shows me the double, the numeric, it shows me the character vector, and then it shows me the list in like this weird collapsed way. And it's telling me that the type of that column is list because it's a list of length 3. And the first element is a character vector. The second element is an integer vector. The third element is a character vector. They have different lengths. That's okay. They can be very different things, but there are 3 of them. So we know this one corresponds to that patient. This one corresponds to that patient, and so on. We haven't talked about this yet because we haven't had really a good use for it, but now that we know how to use map, we can apply map and within the context of mutate on these elements. So we'll see that in a little bit. if we do glimpse on this data frame, you can see a little bit more information. It actually tries to show me my list. It tells me it's a named list actually, because I did name the elements. You don't have to, but I did here. So you see some information about it. And then the other part of this is this nesting idea. So how do we get to this? How do we get to having a list column other than this like awkward manual input? And that's with nesting. So again, these cheat sheets, the tidyr cheat sheet is actually the one to look at for stuff related to nesting. This is from an old purrr cheat sheet that I liked their visualization better than the one they replaced it with. So I stole that. But this idea of nesting, if we think of, let's pretend this is the penguins data. This is actually the iris data, but there's a species column in that data set as well. This is nested based on species. We've nested the data frame so that everything else, all the other data is now in a list column. So it's taken the subsetted data, put it in the first row for everything in this species, Setosa. The second row that corresponds to versicolor species is all the data where species is versicolor, and so on. So up above, we saw split, which took these 3 data sets and made a list out of them. Nesting basically puts that list in a column of your data frame. So it's a little convoluted. I don't know, it's complex, but it's tidy, because now instead of this kind of mysterious list object that could be however long, could contain whatever, now we've put it inside a data frame, so we know exactly what it's corresponding to. We know it's corresponding to species. We could have other information about that data set out here too, that helps us have context to what's in there. And then we'll see that it's actually easy to work with this data like this. So it actually is quite handy. So we can use a nested data frame to preserve relationships between observations and subsets of data. So here we're preserving the relationship between species and the data corresponding to that species. And then once we have it, we can manipulate it using purrr functions like map and map2 we'll see today. So what does this have to do with mapping data frames? Let's nest our penguins data and call it penguins nested. And we're going to group nest on species. So similar to like that picture, and similar to what we did above, but now we can see penguins nested is a data frame. It has 3 rows, but it has this data column. That's the default name that it gives that nested column is data. And then within there is our data frames. You can't really see it very well here. If we look at glimpse, you can kind of see a little bit more. Let's actually view it to see. You can see it's containing a tibble, and if I click on this little spreadsheet icon, it shows me, even shows me the 2, 1, like the accessor numbers that I clicked on Chinstrap, I think. And so the third one, or no, I clicked on the first one. So this is showing me it's a tibble because it's viewing it as a tibble. And I could have said, I just want that column, the list column. So similar to the way we pull out a column that's like a vector of characters, we can pull out a list from that data. So if I run penguins nested $data, I can see it a little better. It's printing those 3 data frames for me. And it looks exactly like that split up list that we did above with group split. And I can ask for the type, the object type, the class, and it's a list. Again, it's that kind of special type of list of data frames. We could also pull out the first element of data, which is corresponding to, if we look at it, this element, the Adelaide row, using the double brackets. And that's just that data set. It's a tibble, 152 rows, 7 columns. Okay, so we have our nested data. It's like, it looks like this, except we have our penguin species here instead. We have our 3 data, and it's in that list column data. So now what do we do with that? So There's also in that old purrr cheat sheet, they had a nice, make this bigger, workflow visualization that I liked. Okay, so this is what we've done so far. We had our data, we collapsed it or nested it into 3 tables in one column. That's what that contains. Now what we're going to do is this mutate map combination. So we want to mutate because we want to add a column, and then we're going to put inside that column the results of a function that we've applied to each of these data sets using map. So map will apply, for instance, this is a model building function. So it applies that model building function to data set 1. The row 1 model output is now the linear model from that data set within that species. The next time it runs it through the second row's data, gives it a model output, puts that in the second row of model, and the third time does the same thing, but in the third species. So we're going to do precisely that, map and mutate. So we want to use our function is called run model that ran our linear model, but we do need to rewrite this a little bit. So if you remember, when we split it up into data, we kept that species column. If we looked at this though, this is one of our data sets in our list column. There's no species column here. You can see glimpse. There's no species. So I can't use that code that pulled out the species name. I have to get rid of that, but it's okay because it's in the data. So if we go back up to look at, yeah, penguins nested here. We don't need to really add in that information because we already have it here. We're mapping our function on this data and preserving the relationship between that data and then the new column that I'm making and that species name. So it's using the species information differently, but it's still all there. So what I did is I just copied that code and got rid of the species part. Now I'm just fitting the model. I just tidy up the results and output that. I'm not like adding a column of species or anything. So it's a slightly different version, simpler version. Run model tidy is the name of the function. And so remember, this is a data frame. So to create a new column, I'm making a list column. I'm going to use mutate. I'm going to create a new column called model out. So I put the name of my column here. And then the first argument of map is the name of the column that contains the data list. So this should be a list column, and this should be my function. Similar to how we use map outside of mutate. We put a list and then a function. So let's run that. So now we have a column that's been added called model out, and it has a tibble in it. And if we looked at that first element, it would be the tidied output from that first data set. And I'll show you, maybe I could save this. Model out data. So if I said I want model out data model out, I can see them. So here are the 3 results from that data modeling, tidy broom tidy results that I got from my function, and I can see them are as elements of that list column. So it's all in there. It's just in a data frame list column format. I do want to say that it might seem like you don't need to use map because we have a function, we have a column. Why can't we just use mutate the way that we learned, where you apply your function on a column and get the model out? That's because this function we made up is not what we would consider a vectorized function. The only thing we can put in this function is one data frame. We can't put in a list of data frames. Wouldn't know what to do with that. We can't run a linear model on a list of data frames, for example. It just would break. It wouldn't know, like if I tried to run this, it's going to give me an error. it can't find my column names because it was given a list and so on. So that's what it's telling me. And so because it's not a vectorized function, we created, it's really hard to make a vectorized function. So it's just easier to make like this one type of function that takes a data frame and then use map. Map will then apply that function to each, what we think of as a row inside our list column. So each element of our list column, row-wise across each species row. So that is just one thing to remember. If you're using the nested data frames, you do need to use map inside mutate. So it's like this extra layer of an application of our function. And what do we do now? So we have this. It's not pretty. You're not gonna print this out. It's not, you can't see it. So what you do then, we've nested, now we unnest. So we go back up to that little visual. Actually, where did it go? I lost it. Here. Then this part, this third part is the simplification. You pull out the information that you want. It depends on what you want to pull out. I want to pull out that whole table, similar to how I did with the split up data set. So what I would do is get rid of the data column. I don't need the data column anymore. So remember, this is a data frame, so I can use mutate, I can use select, I can use filter, whatever, all of those tidyverse data wrangling functions. So I got rid of that column using select, and then I use the function unnest. Unnest is the opposite, the reverse function of group nest or nest in general. There's another function that nests. So what does this look like, just to show you? I have to specify the column names that I want to unnest, which was called model out. What it's done is it's stacked them on top of each other, similar to what we saw from splitting it into a list and then using map DFR on that list. It's the same output. It's the tidy model output from the 3 species stacked on top of each other. So we could do the same thing that we saw above with like making the forest plot out of this data set, or cleaning it up, just pulling out the build depth estimates or whatever. It's a tibble, so you can do whatever you want. You could add GT on top if you wanted, whatever you want to it. Not that pretty because it's not rounded or anything, but it's all there. All the information you want is there. 13 minutes. I think we have time just to get through this up into challenge. So this won't take long, and then I think we'll probably just stop and go over the rest later. The last function I want to mention is map2. So up until now, we've been applying map to 1 list, but you can actually apply map to 2 lists or even more. So there's map2, and then the one I cut off is called pmap, which is in even more if you have more lists. So the idea here is that instead of taking 1 list as an argument, it takes 2 lists as an argument. So your function should take 2 arguments. It should take, let's say, the data and the species or something else, like 2 of your columns, 2 of your lists should go into your function. So we'll see why we want to do that. We're going to use this with our build scatter plot function. So map2 maps over multiple inputs simultaneously. It takes 2 arguments, x and y, .x, .y. They have to be the same length, or you can have one can be a vector of length 1 if you want to recycle it over the length of the other vector, or list. It should really be lists. And then f is a function. So it's the same idea as map, except now you have the first list name, the second list name, and then a function to apply. So in order to use map2 on this data, I'm rewriting my build scatter plot function to take df, the data frame, and species, the name of my species. So instead of pulling it out of df, which we don't have anymore because we don't have a column named species, I'm going to pull it from the nested data set and then call the title again is species. So very simple. It's the same scatterplot plot code. I just, instead of pulling out species from DF, I put it as an argument. So to apply map 2, we go back to our nested. This is our original nested data by species. We create a new list column called plot out. We use map 2. The first argument is the data column. The second argument is the species column. And the third argument is our function, build scatterplot. So if we run that, this code is the same as this code, but without all the extra comments. I find this a little cleaner to look at. Map 2, data, species, build scatterplot. This is the name of my new column. So let's look at that. Uh-oh. Did this work? This was working earlier. Uh-oh. This argument. Real-time debugging. Oh, because I didn't run this. It didn't like, okay, that's why. I was using the old build scatterplot. And so it didn't know how to deal with species. So because I didn't run that, now I'm running my new function. Now it works. Okay, so now we have our plot out. Map 2 was making our ggplots. Now we have a list of ggplot objects. That's kind of cool. Now we have a data list of data, a plot out list of ggplots. And if we want to look at them, we can just call that column and it's going to show us all 3, just like we saw the list of plots up above. It's like a list of plots here. And then before we leave, I want to show one cool function in this package called ggpubr. ggpubr has a function called ggarrange, which will take a list of plots and put them all in the same panel. So just running that. The argument name is plot list. I put that column, penguins plot out, and then it put it all together on what this is one figure. So you could save this as one plot. I use this a lot if you need to put like panel A, panel B, etc. You can add subtitles and change legends and all kinds of stuff. I'll try to talk about more about it next time. You can change like number of columns to 3 and have them all next to each other. But that is a very useful way to just put them all in one figure if you need to. Okay, so I think we'll stop there. You can do the challenge on your own if you want. Maybe we'll talk about that next time. And I will let you know when the final is up on Dropbox, hopefully by Friday, probably by Friday.
Hey, Jessica, so just to be clear, our last final homework was already out, and so the only thing left outstanding now, it will be the project, correct? Is that correct? Or the correct. Final homework project thing.
Yeah, the last homework is due Sunday, so that one's still out there. But yeah, that will be your last homework, and then the final will be due in 2 weeks.
Perfect. Thank you so much.
2 more things. Thanks all.
Thanks, Jessica.
Have a good night.
Okay, have a good one.